I'm very happy to have two very special guests here today. I wouldn't dare to call them nerds because I just learned that geek is the more cool qualification. Caroline de Kok is a geek, I could say. She is a lawyer by training, is the author of iLobby.eu, a survival guide to EU lobbying, but she works a lot on technological subjects and knows almost everybody there is to know and everything there is to know about technologies here in Brussels. So we're very happy to have you here. Second speaker today is Peter van Roste, and he is the general manager of Center, which is a platform of top-level domain names. And we're also very happy to have you here today. So we're going to see your presentations, and then we'll just open up for an informal discussion about the subjects you raised. Thank you.
I first wanted to, when I was asked to talk about the internet, first of all, I'm a lawyer, so I'm geekish, but certainly not an engineer. And that makes it both easy to try and simplify what the internet is and difficult, because lawyers make everything sound complicated, even worse than engineers. And the first thing I thought is, if we think about the internet, let's think about what's going to happen during the next hour on the internet, so that we put things on, in perspective. Over the next hour on the internet, 13 billion emails will be sent. Sadly, a vast portion of those emails will be spam. 1.5 million tweets will go across Twitter. 2,100 hours of videos will be uploaded on YouTube. And 180,000 pictures will be uploaded on Flickr while we sit in this room. That is what the internet is today. And then I'm going to look at first how it came there and how this is happening. So how is this possible? How did this big network become possible? This is my personal opinion, because you can read PhDs on why the internet is what it is. To me, if I summarize it very bluntly, the first reason the internet is what it is because a military motivated invention called ARPANET, created 42 years ago, was opened up first to academics and then to commercial purposes. If that thing had stayed in the military domain, we might never have heard of the internet. But they opened it and they allowed people to talk over it, do e-commerce over it, and the world to get connected to each other. So that's the first reason, I think, why the internet is what it is. The second reason, you're not going to be able to read that, but my slides are on script and on SlideShare, is because this is the letter that was sent by CERN, which is the organization, the European Organization of Nuclear Research, where they put the source code for the World Wide Web in the public domain. And they encourage everyone to use it, adapt it, improve it. So basically, the internet was made possible because all the codes, the underlying codes of the internet, were in the public domain. They were not protected by intellectual property. And that allowed everyone to innovate, to make it better, to improve it, and to build on it. To me, those are the two fundamental reasons why the internet is what it is today. But let's look at what the internet is. We can define it. This is my definition. Bunch of computers and cables linked. It's not a very handsome definition, but I think it says what it is. And it's not a cloud, by the way. I know engineers love to represent anything complex by a little drawing of a cloud, and that makes you think it's very complicated. But it is really this. It's lots of cables that interconnect routers, nodes, servers, call it what you will, lots of computers. It's very complex. It keeps on growing. But that's what it looks like if you highlight it in this way. Talking about the internet, you have to take a definition from Wikipedia, which is always fun. Internet is the worldwide, publicly accessible network of interconnected computer networks that transmit data by packet switching using the standard Internet protocol. It's a network of networks that consists of millions of smaller domestic, academic, business, and government networks, which together carry various information and services, such as electronic mail, online chat, file transfer, and the interlinked web pages and other documents of the World Wide Web. Now, I've highlighted a couple of words in there because I'm going to look what those mean. Because you can read this and think, okay, it's a network of networks. But packet switching, protocols, the World Wide Web, what does that mean in the context of the internet? This is my way of explaining what the internet is compared to other things. The guy that carries the boxes, that's the internet. Those boxes that he's carrying are things like the World Wide Web, the web pages you look at, email, file transfer. FTP is one protocol that is not maybe as well known as peer-to-peer. Peer-to-peer is quite well known. It's one of the protocols used by BitTorrent, but it's also one of the protocols used by Voice over IP, for example, in certain cases. And he also carries instant messaging, chat. So people tend to think that the World Wide Web and the internet are the same thing, the web and the net. But actually the World Wide Web is a part of the internet. The internet is bigger than just the World Wide Web. And under there, under the internet still, you then have the infrastructure, the cables, what we call the telecoms operators or the mobile operators. That's still one layer down. So infrastructure, it's as if you have the street. The guy that walks on it is the internet, and the bags he's carrying is World Wide Web, email, and so forth. Because there are those many layers, that means you have a lot of different players on the internet. Now this is a chart by the OECD, which I thought was interesting. I mean, you have so many ways of classifying them, but basically you have what they call the internet access and service providers. In the old days of the internet, those were separated. You had internet access providers and you had a lot of ISPs. I think these days you have more and more consolidation. So the internet access provider is also your internet, your ISP basically. If you're in Belgium, for example, Belgacom is both your internet access provider and your internet service provider, or Telenet for that matter. They can be fixed or mobile. Your mobile network operator is an access provider to something that they call the internet, even if it might not be the internet at the end of the day. But that's the underlying structure. You then have the web hosters and the content delivery providers. Those are the people that store data, but it's not their data. They're storing it for someone else, for content providers. If you have a blog, for example, and you have it on your own domain name, you will host it with a web hoster. If you're a normal person, that will be on a shared server where lots of people host their websites. If you're a rich person, you will have your dedicated server, for example, which is your own server with only your content on it. And in some cases, for some companies like banks, we're not talking one server, we're talking about racks of servers where all of the data is stored. And then the next type of intermediaries you will find on the internet, search engines, Google, Bing, e-commerce intermediaries, eBay, Amazon, Priceline. Payment systems, also important intermediaries, Visa, PayPal, and what OECD, that must be OECD language, calls participative networked platforms. That's social networks, by the way, in normal speak. Or Web 2.0, it's Facebook, it's YouTube, it's all of those players. And then a bit outside of the internet world, but still big contributors to the interest of the internet are the content providers, as in companies that produce content, newspapers, Walt Disney, I don't know. And then users who are increasingly becoming content providers by blogging, by sharing their pictures on Flickr, by sharing information on Facebook. So that's kind of the whole ecosystem of the internet. And the reason I'm showing that is partially to show how confusing and complex it is. I mean, the internet is like walking into a giant shopping center and you know, looking at all the different players doing different things. So whenever you think of, when people talk about regulating the internet, I always think, oh my God, that sounds like a very, very tricky thing to do. Because there is no such thing as one single identifiable internet player. There's a vast multitude of different people doing different things. Okay. In the Wikipedia definition, they also talk about something called packet switching. Now, there's two big types of switching. In the POTS, what the geeks call the POTS world, which is plain old telephony services. Yeah, that's how we call it. In the POTS world of traditional telephony, the system used was circuit switching. That basically means that the communication flow follows a path that is selected beforehand and that remains fixed during the session, and that path is dedicated. Now, that doesn't mean anything to you, so I'll show it on a drawing. What that means is, in the old telephony world, and still in the current traditional telephony world, when you pick up your phone and you call someone, the whole time of your conversation, when both of you have the phone off the hook, that line is busy, and it's used only by you. No one else can use it at the same time. That also means that that line is the way you speak over the line. All of the words come across in one session, in the right order. Nothing is tampered with. It just goes through nicely. And, you know, if you say, this is the famous sentence, "Mr. Watson, come here, I need you," which is the first sentence that was ever said by Graham Bell over a telephone line, it just comes through like that in one connection over a circuit-switched network. As you can see, it's a bit like if you brush your teeth and you leave the water on all the time, you know, even when you're not putting your toothbrush under, the water is just running. It's nice because you never have to put the tap on and out, but on the other hand, it's not very efficient and you're wasting lots of water, basically. The alternative to that the internet put in place is called packet switching. That is a system whereby the network splits up every communication that you want to do in small packets. And then it just throws it over the network of networks in a random order. It's like chaos. They just take it and they throw it, and it takes all the routes that are available at that point. And at the end, all of these packets arrive at the receiving computer, and he puts the puzzle back together. So before looking at what that means in terms of network, quick word about what a packet is. A packet, you have to imagine, it's like you have a box, and in there there's smaller boxes, and it keeps on getting smaller. And if you look at that box, it gives different types of information. There's what they call a header, data, and a footer. And the maximum size is usually 1,500 bits. So it's quite tiny that they have to slice it up, each piece of communication. The header gives information about who is sending that communication, where it needs to go, what type of data is in there. Is it video? Is it voice over IP? Is it an email? It also gives the packet number, which is handy if you come at the other end and you have to put them together again. It's nice if they're numbered. The data is the part where your actual communication is. So if you're sending an email, it's the content of your email sits in the data. And then you have the footer, which has mainly two purposes. One, it shows that that's the end of the packet, so that the computer understands, okay, it begins here and it ends there. And secondly, it has some neat applications for error correction, because the problem that you have, obviously, when you throw all of these packets over a network of networks, and that can go across, you know, continents, countries all over the place, is in some case, they drop a packet. A packet gets lost somewhere, or it comes and it's been a bit tampered with by the network, so it's not readable. The footer allows the computer at the end to say, whoops, that doesn't look like a decent packet to me, send it again. And then that packet will be resent by the sending computer at the beginning. Now, this sounds all complex, but this happens in milliseconds. It doesn't even take seconds for all of that to happen and all of those conversations to go. And I put little zeros and ones because all of this is in binary. It's all ones and zeros. That's all that it looks like. It's gibberish. That even having worked at a telecoms operator, even there, only very few engineers can make sense of what all those ones and zeros actually mean if you have to retranslate them into real words. In terms of policy discussions, this is, packets are things that you discuss when you talk about deep packet inspection, for example. When networks start doing traffic management or want to make products more tailor-made to what you do or things like that, they go beyond the header. Basically what they do is they don't just look, is this packet video? They look, what video is this packet? Is it YouTube? Is it Dailymotion? Is it somewhere else? That is not normal in the current internet, normal procedure, because that was not needed. But it can happen if you want to start blocking or throttling certain services and give preference to others. In the normal logic of the internet, the reason why you just want to know if it's video or if it's email, for example, is because video, or let's take voice, which is even a better example, voice over IP requires your packets to go reasonably quickly at the other end, because otherwise the voice is cracking. You don't hear the communication well. If the packets don't go smoothly, if they're kept in a router for a couple of milliseconds, then that conversation will be a bad one. And that's when you usually go, if you're on Skype or whatever, you go, God, what a crappy line I'm having. But that's just the packets that didn't go through the right way, or could be other reasons. Whereas email, it's not that important. You sometimes, if you send a big email out of your Outlook, for example, if you use Outlook, you will see that it's in your outbox for a couple of seconds. And if you want to click on it because you just realized you shouldn't have sent it, it says, no, it's busy sending it. That's because, those couple of seconds of that email going through and those packets going through, it's not that important for email. It doesn't make a big difference for the persons receiving it. So that's the reason why in the header it was important in the logic of the internet to know what protocol are we talking about. And I'll talk about protocols afterwards. So, looking at packet switching, this is what happens. If you have a sentence that says, Mr. Watson, come here, I need you, that gets split up, and I need you, Mr. Watson, and come here are just thrown all over the internet with their little headers and footers as packets. They follow all kinds of routes, the ones that are free, the ones that are shortest, all depends on the moment of the day. And at the end, it gets put back together, and you have your end message in order again. Protocols, mentioned them when I talked about packets. When you have a network of networks all across the globe, all of these computers that are interlinked need to be able to talk to each other. And protocols are basically languages that make sure that they understand each other. And at every level of the internet, you have a variety of protocols that allow computers to understand each other and to share information. One of the protocols that you all know, but maybe you didn't realize it was a protocol, is HTTP. When you type and you have maybe a browser that doesn't identify just directly typing www. And you have to type the HTTP and the 2 backslashes. That's a protocol, actually. It's a protocol that allows web browsing. There's other more obscure IP internet protocol, you will know it, that's at the network layer. FTP is for file transfer. I mean, look at the slides. It's at every layer of the network, there are different protocols that allow all of those computers to talk to each other. And then there's a different element that is added to those protocols, which is that these protocols go through what is called ports. And there's no boats involved, sadly. It's gateways, it's openings. I don't know how you can define a port, but basically the logic of a transmission is, depending on what you want to do over the internet, you will use a certain protocol and your communication will go through a certain port on your computer and on your router. The reason I'm mentioning that is because with all those different elements on the internet, those are all places where traffic gets blocked, for example. If you think of certain policies of internet access providers, They might decide that they don't like peer-to-peer because they associate peer-to-peer to BitTorrent and illegal downloading of files. They might act at different levels to avoid you using peer-to-peer. They might block the protocol, or they might look at the port that is used by the protocol and block that one so that you can't have communication. In many cases, you won't even be aware of it. They might have told you somewhere in the terms and conditions, but who knows what the port for peer-to-peer is. I must admit I got, I think it's 18 months ago, a letter from my access provider that said, for your safety, we are going to block a whole list of ports, some of which I had never heard of before, and if you don't agree, please contact us. I just looked at it and I thought, oh my God, if my mom receives this, she must be really scared. And then I Googled all the ports, to be quite honest, to see what they were doing, and decided I disagreed with it because one of the ports was the one I used for Skype. So I was kind of annoyed that they would block my Skype port. So all of this technology that was used to make internet logical and allow it to function across the globe also allows it to be tampered with to a certain extent, and to be to choose in terms of traffic management what you can, what you allow to let through and what you block or you throttle. Throttling means that you put it in the queue in a router. When lots of packets come at the same time in a router, some get priority and some are pushed back and wait a bit. And if they have to wait too long, they're dropped. All of that can be done by using these different elements. So, but the big question is, what happens between when you type ft.com and you get ft.com on the internet? And I made a drawing. Very proud of my little drawing. And that's a nerd, by the way, Marietje. That's what a nerd looks like. It's the glasses. So basically, when you type ft.com, what it does is your router goes on the internet through your ISP. And what it does is it asks all of the servers, and you will go in more detail on how they ask that. It says, where is ft.com? And then at some point, one of those servers will say, well, it's actually on that IP address, you need to go there. So your query to say, where is ft.com, goes all the way to the server of FT. And there, FT gets your request, and let's say that you asked for ft.com/international, because you wanted the international news. On the server of FT, there's huge databases that usually split up things like the images, the text, maybe videos that are on there. So when they get your query, they say, okay, what's appearing on that page? And they collect it from the database and put it together in a string of IP packets. So you get lots of 1 and 0s that are put together and that reflect text that is in HTML, that reflect how the page should look like, which is called CSS usually. It's cascading style sheets. Those basically say, well, the background should be kind of, what color is the background of the FT? Orangey, pinkish, kind of. There should be boxes there, and the banner should be on top, and the text should appear there. There's, video files. All of that goes into your lovely little packets, and then they go back to your PC where magically the page appears with all of that information. That takes, yet again, milliseconds for it to appear. Oddly, in some cases, you can actually see the fact that all the packets don't arrive at the same time, because when you download a page, for example, the text may appear before the images show up. That all shows that it's puzzling it together. And the way this is puzzled back together is with your browser. Internet Explorer, Firefox, Google Chrome, Opera, depends on what you're using. That is your translator of those 1s and 0s into something that makes sense to you as a human being. And that, I think, is pretty much it. Oh, that was my disclaimer. You need to read it when you have time, if you go on the slides. It's my disclaimer about me being a geek but not a nerd, and the fact that all of you are listening today, turning you into geeks too. So that was it for me.
Thank you very much.
Thank you, Caroline. That gives me an excellent basis to give you a quick update on one of the lesser known but pretty interesting parts about how the internet functions, which is the naming and addressing. The reason why probably nobody knows, or most people have never heard about the domain name system, the DNS, or the naming and addressing issues is for two reasons. First of all, it works. So that means nobody complains, nobody cares. And secondly, it's run by a not-for-profit sector, which also means that we don't appear in newspapers about profit margins for the last quarter. Not-for-profit sector means that what you pay for your domain name, if you have one, is basically reinvested in the local internet communities in terms of research and development to work on the next level of the internet. So let me get started. First, I have a question. How many people in this room have a domain name? Okay, that's not too bad. Caroline mentioned IP addresses. Okay, yes, third levels do count. First of all, a quick step back. Caroline mentioned IP addresses. As you know, the internet consists of devices that communicate with each other. I mean, obviously, to do that, they need to know where to find each other. And that means they have to have an address. Currently, we're using two types of IP addresses, version 4 and version 6. Why is this relevant? Because version 4 is running out, and version 6 is being introduced, and it comes with a whole range of technical, but also policy and legal issues. And this is how they look. An IPv4 address you're probably familiar with. It consists of 4 groups of maximum 3 numbers. An IPv6 address is much more complex, but it also means that there are many, many more of them. Having a look at the benefits, IPv4 is compatible with any device that we're using at the moment. Your mobile phone, your Wi-Fi router at home, the servers in your office, your desktop and laptop, obviously. So IPv4 is what everybody is using right now. IPv6, which is being introduced, has the advantage that it's much more secure. It's more stable. Because they can do much more clever things with routing compared to the IPv4 system that Caroline explained. And IPv4 is running out, not just because there are not that many of them, but because there is an enormous boom in the use of IP numbers, IP addresses. Even your car probably already has IP addresses, which are now communicating with your car key, and in the future will be communicating wireless with your car repair shop. If you look at the number of addresses that exist, I've written them down there in numbers, but frankly that doesn't mean anything to anyone. This is what it looks. If you would assume that the number of IPv4 addresses has the size of a golf ball, then the range of IPv6 addresses has the size of the sun. So it's clear that from now on we should not be running into any scarcity anymore when it comes to addressing. So why do you need a domain name if you have addresses which allows the devices to communicate to each other? There are 3 very basic reasons. First of all, nobody is able to remember long IPv4 addresses, let alone IPv6 addresses. So it's easier for people to communicate. It's a mnemonic. You wouldn't remember an IPv6 address for a website, but since they're also used for email, it would be pretty hard to communicate your email to your counterpart in a discussion. Secondly, domain names allow the system to become flexible. If anything would happen in a worst-case scenario with the server on which your information is hosted, it would be pretty easy to switch in the domain name system the IP address that is referring to your content. So it makes it more flexible, and it also makes it more secure, since it's easier to distribute packets in case of a server overload, which most of the time would happen through malicious conduct, such as a denial of service attack, basically hackers trying with millions of them to bring your server down. So this is what, and unfortunately I only used IPv4 addresses here, but this is what the addresses look like. And I'm sure most of you will have visited one of these sites very recently, but obviously would know by only looking at the IP address. So it's the website for Europa, and the most popular websites and email addresses in some of the member states. So that's a pretty good reason why we need domain names. How does it work? We have a 1 minute and a half movie, which I'm just going to show you, and it's probably the easiest way to get it across.
Computers and other devices use IP addresses to identify each other on the internet. As we can't always remember complicated numbers, we use words instead. The domain name system brings the two together to get you to your destination. This is how it works. All around us we see domain names. For example, the website of your favorite band. The site is stored somewhere on the internet. Let me explain how your PC finds it within milliseconds. The journey starts with typing in the website address. In words, of course, as you wouldn't have remembered IP 88.151.243.8. Your device will read the address backwards. It will start at the end with the root domain, in our case, .eu. Information on the root domains is stored in 13 different root servers located around the world. In reality, there are numerous more copies of each of these machines in different locations to make sure that whatever happens, the system will keep on working. A root server contains the information on the name servers for the different zones. In our case, it tells us where we can find the information on addresses ending with .eu. Again, for reasons of security, there are a number of these .eu name servers located around the world, so that if one is too busy or stops working, for example, due to an earthquake, the information would still be reachable elsewhere. The .eu name server knows where the information for the more than 3 million .eu addresses is stored, and will tell us where we can find Flaming Flamingos.eu. It will communicate this unique IP address. The IP address for the Flaming Flamingos website is now identified and sent to your computer. Now the download of the content can start. But remember, this whole process that makes it possible to connect your computer to the place where the website is stored happens in just a few milliseconds before it connects to the internet and starts downloading the information. In reality, a lot of this information is stored along the road in the so-called cache memories, so that it can be retrieved faster. This movie is brought to you by...
Okay, well, that was slightly awkward since the coloring of that projection left out some of the crucial bits. But I hope that you still got the key message. It's a hierarchical system. There is one type of file which is unique, but there are many copies of it. But it's identical, those copies. And those files are spread across the world. And when you start downloading information, you first are going to figure out where that information is coming from. And that's what the domain name system is doing. So just running you through some of the key aspects of how it works and who does what. Because it's pretty relevant when you start thinking on who governs the internet and who decides on some of the policies. Key players are the registrant. The registrant is basically you. It's the owner of the domain name. You're the person putting content on the web. You're going to register that name with what is called a registrar. It's an intermediary, so an entity that mainly sells domain names, but would typically be also involved in hosting. It could even be your internet service provider who can sell you domain names. And then the registry. The registry are basically my members. You have one of them for each country, and they will manage the zone file for that particular country. So for Belgium, that is dns.be. For the Netherlands, it's SIDN, who's running .nl. For the .eu extension, it's URIT, an organization that's under contract by the European Commission. ICANN is the organization that coordinates the global policy for the DNS system. And IANA is the organization that actually manages the top-level zone file. So this looks a bit like this. On top of it all, you have the root zone. In the root zone, it's a pretty simple file. It has about 350 lines in it, and that each line will identify the next level, which will be a country code top-level domain, such as .eu, .be, .de, etc., or a generic top-level domain, such as .com, .org, or .net. Then you have the registrar. EuroDNS is one of the many that will help you buy a domain name in Europe. And then you have the registrant, which is yourself. The root zone, as I mentioned, 30 identical copies, and they're managed by different organizations. This is relevant because it means that there is no single entity or no single point of failure for the internet. You would have to corrupt 13 of these files and bypass all the incredible complicated security measures that are being taken to actually affect any of the traffic in the internet. Those 13 copies are named A to M. IANA operates them under a contract by the US Department of Commerce. And probably the most important point in here is that any change to that copy requires approval of the United States Department of Commerce. So that means if the file for .eu needs to be adapted, then the US government will have to approve that. And without that approval, that change is not going to happen. The root zone has 323 entries, 21 are GTLDs. Com, org, biz, net, info are the most well-known. You have some obscure like museum and .coop and .pro, but they are not that much used, definitely not in Europe. There are a couple of test domains. Very interesting, since a year and a half now, we have non-Latin scripts in that root zone. This is the top level for Singapore. We have 37 of those internationalized domain names, as we call them, rather Latin-centric, in there at the moment, and it's growing rapidly. The most successful one is in Cyrillic.rf. I think they hit about 1 million domains at the moment. And then you have the 254 regular country code domains as we know them at the moment. Just to put this in the proper perspective, this is a very relevant bit of information when you're discussing internet governance. Who is responsible for what on the internet? It's especially relevant when from a law enforcement and cybersecurity perspective, people are looking at addressing, combating illicit activity on the web by addressing the domain name system. So without a proper understanding of how it functions and who controls what, this might turn into a waste of time. Just to give you a visual of how the distribution of that root zone across Europe looks, the numbers are the couple of occurrences in one place, but in general you can safely say there are about 80 occurrences of that root zone, that very important file that I mentioned to you earlier, in Europe, managed by many different organizations. Within Europe there is the best interconnection between registries, so the operators of the top levels. There are excellent contacts between .fr and .de and .uk and 25 others amongst them to make absolutely sure that when anything would go wrong with a zone file in one country, the other countries can step in and help solve the problem. That's why, at least until the moment, we've always been able to connect to any domain at any point in time since the start of the internet. CCTLD, so those country codes, at the moment there are 80 million worldwide. There are about 200 million domain names in total. Important point is that the CCTLD policy, who gets a .nl domain name or who gets a .ie domain name, are set nationally. ICANN nor the US government has anything to do with that. CCTLDs have 4 tasks, so they num the resolution, they run the resolution service. If you type in a domain name, you will get to your destination. That's probably a crucial role that they'll fulfill. They allow to add additional names to that zone file, so it's a registration service. It's also a directory service. If you want to find out who owns a domain name or who owns a email server, you can find it out by using the whois. And for those who might not have the pack yet, I brought with me some position papers which go a bit more in detail on some of those, and whois is definitely an important one of them. This is a whois, by the way. This is what it looks, and I'm not sure if you can read it, but at least you get an ID. If you go to IANA on the top level, and you type in a query for a CCTLD, you will get something similar. This is a query I did on the whois service that's run by the operator of .org. It's very simple. You just type in whois.org on any search engine, and you will end up on the whois for that domain. And then you type in that window that will be provided to you, you type in the domain name that you're looking for. So this is the whois query for center.org, our own domain. And it lists the owner, which is us. It gives the address, the telephone number, the email address. We're a business, so obviously we don't care too much. And on the contrary, I find it quite handy that people can always get in touch with us by looking up the whois information if they wouldn't find it on our website for some reason. But this has obviously implications for the whole privacy and data protection debate. And that was basically my short overview. If you have any particular questions, I think we have now some time for public discussion.
Thank you very much, both of you. That was a lot of information and very concise and nice presentation. So thank you very much. I just want to go around the room and gather one round of questions, then we'll do answers, and then you can all get on with your day. So who has questions? Yes.
Yes, I have one remark and one question. So there's not even one for each person. The question I have is, why is it that Catalonia has its own country code, but Flanders, for example, does not have that?
Right. As I mentioned, ICANN is the coordinator of the global policy that runs the top-level domains. So there's 323 names. ICANN started about 10 years ago, and they started off with using a list of country codes, which was developed by the UN. They used the ISO list for the country codes. If you're not on there, you will not get a country code. And then they created the generic top-level domains, as we discussed, com, org, biz, net, etc. About 5 years ago, they started with another round to expand that generic top-level domain range. And one of the applications was from a cultural TLD, which was .cat. So they were approved in that particular round. And at that time, there were no other candidates for that type of domain. So .cat was introduced more or less as a sort of test on how successful and viable this type of domain would be. As some of you might have picked up, ICANN is now about to launch. They have been about to launch for the last 3 years, but now they're getting pretty close. The new round of generic top-level domains. So in about a year or two's time, you would be able to see .car, .mobile, .parliament, but also .cot and .flanders. So in the next round, these would definitely be possible. But in the meantime, ICANN has simply not approved any other additional generic top-level domains.
I also have a question to Caroline, because I was fascinated when you were talking about the packets and then how deep packet inspection works. And as people who work in a parliament, we're constantly confronted with who makes which decisions about which part of the information that flows around on different servers and devices, and who is responsible, who has the oversight. Could you explain in the process of where data goes, what happens when and who takes action when net neutrality is broken, or when censorship is imposed? Yeah. Where does that come in, and who decides on that? Yeah. I know it's a difficult question, but I think it relates a lot to the decisions we have to make here.
Well, obviously, when you have, first of all, censorship and net neutrality uses pretty much the same tools, so I'm not going to differentiate much in terms of tools. It's just that the decision-making process is done in different places. With censorship, you often have governments or public authorities deciding. With network neutrality breaches, you often have commercial entities deciding on what is allowed through or not. But in terms of tools, it is often pretty much the same tools. What happens is there's two ways of hindering access to information or stopping flows of traffic. You can block them. That is obvious, that's easy to spot. You try to get on a website and it says, as you would have, for example, in China, in certain cases, you have a warning in Chinese telling you this is not authorized to access the site. You know, that's straightforward, you know it, it's blocked. In other cases, and those are more cases of commercial tampering or traffic management, depending on which side you're on, they will not block, but they will degrade access. That's where they install softwares or applications that basically identify packets they do not like, but allow a certain percentage of those packets to pass and will drop another percentage. For example, if you have a Skype conversation, they might decide that 30% of the Skype packets are dropped and 70% go through. That's enough for you to have a conversation over Skype, except you will be cut off constantly and you will only hear pieces of sentences when they talk. The levels at which they intervene are variable. As I said, port blocking is an easy one. If you look at your mobile phone, often there's lots of ports that are being blocked standard on your mobile phone to avoid, and in your contract it often states you're not allowed to do peer-to-peer, you're not allowed to do voice over IP, you're not allowed to do, in certain cases now in the Netherlands, instant messaging. And for you to be, to make sure that you're not doing it, they can block the ports that would allow you to do it. Now, some very geeky technical people might try to bypass that. You know, congratulations, but most normal human beings will just be stuck with a phone that doesn't do much. Protocols are also a way of spotting certain types of conversations you don't like, as I gave the example of BitTorrent and peer-to-peer. The sad thing about peer-to-peer is that it got a really bad name because of file sharing practices on BitTorrent. But it's a great protocol that is also used by CERN, for example, the European Organization of Nuclear Research, to put the capacity of all computers they have within the academic area together when they really need a lot of processing power. So peer-to-peer is actually a really neat protocol. It's not the most efficient one anymore on the internet because it uses quite a bit of capacity, but it's a great way to use a lot of capacity on a network. So they might tamper with that protocol, and I'm pretty sure they might. I mean, the interesting or the sad thing, I would say, on the internet over the past decade, I think, is a lot of energy has been put in by certain players to try and control more and more what goes over the internet for legitimate and illegitimate reasons. In some cases because they're asked by police or law enforcement authorities, in some cases for commercial motivations. So they're putting more and more energy into creating softwares that are called sniffing softwares. They sniff packets and they identify them and they drop some. Creating deep packet inspection that makes you go beyond, is this video or voice, but makes you go at the stage of, you know, what video, what voice, is it Skype, is it my own, is it someone else's? And at the same time, there's equal energy put by the companies that provide a lot of applications and services to disguise their packets. There's actually teams of engineers that do nothing else than to make a VoIP packet look like something else. They might make it look like email, they might make it look like... I mean, they're basically putting little disguises around the packet so that the routers, when they go through, think, hey, wait a minute, this is not Skype, this might be something else, or this is not, you know, a Google query, this might be something else, or a YouTube. And to me, it's fascinating to see that the amount of energy put in that could be put in creating new products rather than doing guerrilla of, you know, I'm looking for your packet, and the other guy goes, well, I'll disguise my packet. And yeah, it's interesting to see how very straightforward, smart, efficient ideas are now being used in ways that, to me, are a bit of a waste of energy to a certain extent.
Thank you. That's very clear. Isn't it also true that the domain names have now become subject to discussion and possible censorship because some of them are deemed inappropriate, or is that not related to the domain names?
Yes, indeed. Well, there are two parts to that discussion. First of all, there is a discussion on what domain name is appropriate and which one isn't. And that discussion is taking place on many different levels. When I mentioned that ICANN is going to introduce new GTLDs, so new generic top-level domains, some people might be seriously offended by a domain name .god. So that's one part of the discussion. Other people not liking domain names that will be introduced on a top level or even on a second level. The other part of the discussion is people willing to remove content by removing the domain name. And as I just explained, and I hope that was clear, that does not make any sense. Because if you would type in, and try it at your desk later on today, if you type in a IP address, you still get to that content, whether the domain name is still there or not. Domain name is not made, it was never intended to be able to block content by blocking a domain name.
I have another question on the TLDs. You mentioned the fact that indeed, I mean, ICANN is now pushing for probably the last time, despite some opposition from the GAC, so the states, this extension of possibilities for GTLDs. What's your view on maybe some risks of balkanization in the end? I mean, what's the maximum number of GTLDs that you have in mind? I mean, I know that's been discussed, and also the fact that it also maybe bears a risk of going a bit too much into business state of mind. I mean, you said that the architecture is not for profit, and that's the case of ICANN, but in the case of VeriSign, for example, I mean, they have a quotation in stock market. So, I mean, that can have a big impact if you have big players who think that it's a good way to make money and to push for creation of ever more top-level domain names.
Yes, thanks. First of all, when I was talking about not-for-profit, I was mentioning specifically the CCTLD world, so the country codes. Indeed, the majority of the generic codes are run by for-profit companies. There is no, at least that's what the reports tell me. I'm a lawyer as well, I'm not an engineer. There is no technical reason why the root zone would become unstable if we would multiply the current number of top-level domains by a factor of 10 or 20 or probably even 100. So technically there does not seem to be a problem. Talking about balkanization, I don't see a risk here for balkanization. I see a risk of some generic top-level domains just failing because there are so many of them that people will not particularly be interested to use a .mybike. And I've seen already quite silly proposals that I think will simply not be viable. So it's not a risk of balkanization. I think we passed the risk of balkanization when we introduced the internationalized domain names, because that was a risk that the Russian government and the Chinese government were not prepared to wait any longer until the West would allow their domains to be entered into the root. And they were already testing their own version of the internet. Well, at least their own version of the domain name system. And that was the balkanization that came very close to ruining everything that we've been working on for the last 20 years.
Okay. On that note, I want to thank both of you for your hard work. I learned a lot, but it also certainly opened up for a lot of more questions, because it's really quite complicated, and it's something we have to keep learning about, and we will, because this is only the first in a series of 4 in total of Nerds in the Parliament. I'm very grateful to both of you for making available your slides so that people who are watching later on the video can also see your presentations. I think that will be very helpful, and we'll make sure that they're easily available. And while you said that there were real risks of ruining everything that had been done in 20 years, I'm afraid we still face some risks in keeping the internet a place for freedom, for opportunity, and for prosperity. And we'll have to keep on working for the next 20 years to be equally constructive. But thank you all for coming and participating, and I hope to see you again in the next series, and do spread the word and keep in touch, and thanks again for your presentations.